what is Cauchy's integral formula? For that I have wrote how it is defined. So it is if f of z is any analytical function within and on a closed contour C, we have to, and if A is any point within C. So we have to see the main difference is the point is within C. Then f of A, which is the point which is inside the contour C, will be defined by 1 upon 2 pi integration on C f of z, z minus a dz. So for proving this, what we want to consider is a closed contour which is C, and we are essentially taking the point inside A. So now to prove this, we will be assuming a circle C1. So here we have assumed a circle C1 with point A, which is the A is the point which is the center of the circle, R is the radius, and Z is the point on C1 circle. So as we know, the equation of circle C1 will be mod of Z minus A is equals to R. So if we remove the mod, it will we can define it as Z minus A is equals to R e to the power of iota theta. So if we take A on the other hand side, so it becomes Z is equals to A plus R e to the power of I theta. And if we differentiate it with respect to theta, we get dz is equals to A being the constant will be 0, and R and e to the power I theta will be I, e to the power of I theta, and I theta will be I, and then d theta from the other side will take. Now here, and we will be numbering this equation as first and this equation as second for future use. Now this equation is for circle C1, which is the smaller circle, and it is around the point A. But the equation we have found was for circle C1, but we have to find it for C, because essentially we are doing it for the point C. So for that, we will be using Cauchy integral theorem for multi-connected domain, an extension of Cauchy integral theorem. It says integration of C, the C, f of z upon z minus a dz will be equal to the integration of circle C1, f of z upon z minus a dz. So both of these values will be equal. Now from earlier we are putting the values of z dz into this equation for circle C1, because for that we have found. So which is equals to, in place of z we will be keeping a plus r e to the power of I theta within f divided by z minus a. The value of z is a plus r e to the power I theta. So a and a gets cancelled, so we are left with r e to the power I theta multiplied by dz. We have found dz also, I e to the power of I theta. So what we are doing is, we will be cutting both of these, r e to the power of I theta and r e to the power of I theta. So we will be getting f of a plus r e to the power of I theta d theta, and I is the constant part, so you go outside. And we know that this circle is around the contour C, and essentially because already R part is cut, so we can say that this R is not determining the value of f of A. So for that, what we can say that if R is very small, then A will be very close to Z will be very close to A. So we can say f of A will be equals to f of Z. So same thing, we will be putting R equal to 0. So this part will become 0. So we are left with f of A d theta. That is what I have written. Now f of A is the constant part, so it will go outside. and we are left with integration on d theta. So if we integrate d theta, so we'll get theta, and because C1 is a circle, so we can integrate it from 0 to 2 pi. So after that we have I f of a into 2 pi minus 0. So 2 pi minus 0 will be 2 pi, which will be this side, which will be 2 pi I f of a. So now this part is equals to f of z, z minus a on c. Both of them are equal. So we'll be taking this 2 pi I, the constant part, on the right hand side, which is f of a equals to 1 upon 2 pi I integration c f of z upon z minus a dz. So therefore we have proved